So imagine a single typo, like an accidental spacebar tap, just completely wiping out an entire company's database in 3 milliseconds, all because you had the wrong privileges.
Oh, yeah. It happens way more often than people think.
Right. Well, welcome to our tactical breakdown of Linux root security, where we are using your provided blueprint and quiz intel to really help you master super user access for both the exam and the real world.
Yeah, we have a lot of ground to cover.
We do, so we're jumping straight into the material. Looking at slide 1, which is titled Linux Root Security, Mastering the Super User Blueprint.
It's a great starting point, yeah.
Yeah, looking at this heavy, impenetrable bank vault on the slide, it really sets the stakes here. Root access isn't just, some administrative toggle.
No, not at all.
It is a skeleton key. It bypasses every single kernel-level security check in the entire operating system. When you have root access, you own the vault.
You absolutely do.
Yeah.
And to understand how that skeleton key actually works, we have to look at how the OS handles identities at the architectural level.
Okay, let's go to the next one then. Slide 2, titled The Master Key to the Facility.
Right. So you probably already know that standard users have user IDs or UIDs that start at 500 or 1,000, depending on your Linux distribution.
Sure, that's pretty standard stuff.
But looking at the quiz intel here, there's an absolute rule you need to know for the exam. The root account is created during installation, and it always, without exception, receives the account number 0.
Wait, really? Why is it hard-coded to 0?
It's a kernel thing.
It just feels almost primitive, for a modern operating system to rely on a single static integer rather than, like, a dynamic security identifier or a hash token.
Well, yeah, but it goes back to the very foundation of Unix. The kernel actually doesn't care about the word root or any usernames at all. It literally only reads integers.
Oh, wow!
Yeah, the authorization routines of the kernel literally have a check. Like, if UID equals 0, hard-coded right into them to bypass permission check.
That is why.
I know, right? If you somehow managed to change the root UID to a 1, you wouldn't be root anymore. You'd just be a regular user.
So 0 is the actual skeleton key, not the name.
Exactly.
Okay, here is a challenge for you, the listener. Take a moment to pause this audio. In 2 to 3 sentences, why do you think Linux explicitly assigns the number 0 to the root account across all distributions, while standard users start at 500 or 1,000? Write down your thoughts on the architectural reasons behind this.
It is a really great question to reflect on because, understanding that the kernel only respects integers, it completely changes how you view system administration.
Yeah, it really does. Now, knowing you have that ultimate power, the temptation is to just use it constantly.
For sure. Which brings us to a major operational pitfall.
Right, on slide 3, titled The First Rule of Incident Response. Okay, let's unpack
This
this.
classic scenario, right?
Exactly. Say servers are crashing, and you're the sole admin fixing system-level problems all day long. Doesn't it make sense to just log in as root first thing in the morning? It seems incredibly inefficient to keep elevating and dropping privileges every 5 minutes.
See, that perceived efficiency is exactly what the slide highlights as the certification trap.
Ah, the trap.
Yeah. Logging in directly as root means every single command you type is executed with that UID 0 authority.
So no safety nets at all.
0 safety nets. A misplaced wildcard in a standard remove command will recursively delete everything from the root directory down. You always log in as a regular user first, so your default state is restricted. Then you elevate.
I get the blast radius argument, I really do. But if I'm doing 50 admin tasks a day, the risk of a typo exists whether I'm elevated permanently or just temporarily, right?
True, but temporary elevation forces a psychological gear shift.
The gear shift.
Yeah, when you have to explicitly type a command to elevate your privileges, you become hyper-aware that your very next keystroke really matters. It prevents administrative fatigue from basically destroying the infrastructure.
That makes total sense. And that forced gear shift requires specific tools. Let's look at the first method on slide 4, titled Method 1, Identity Theft via SU.
The SU command, yeah.
Although, I gotta say, I take issue with the theft part of the slide's visual. You aren't stealing someone's locker combination. I'd say you are borrowing a disguise.
I like that. Disguise is a much better way to think about it.
Right, because the SU command, which stands for switch user, requires you to know the target user's password. You are willingly putting on their uniform.
Exactly. The strict mechanism of SU is that authentication is tied to the target. To become user JSmith, you type SU JSmith, and then you provide JSmith's password.
Not your own password.
Right. The authorization module checks the target's credentials, not yours.
Okay, and if root is switching downwards to a standard user, there is no password prompt at all because UID 0 just bypasses that check entirely.
Yep, root can become anyone.
But here's where the exam gets tricky with the syntax. Listeners, think about this before we reveal the answer. If you just type the letters SU at the command prompt without specifying a username, what does the system assume you are trying to do, and whose password will it demand? Pause the audio and formulate your answer.
So the underlying mechanism here is that the su command has a hard-coded default target.
Which is?
If the target argument is left blank, it defaults to UID 00. It automatically assumes you want to become the super user, so it will immediately prompt you for the root password.
It assumes you want the big chair.
Exactly.
Speaking of chairs, becoming root isn't just about the permissions, is it? It is about the actual environment you inhabit.
Oh, environment variables are huge here.
Let's move to slide 5, titled The Environment Matrix. Decoding the dash, which explores this. I kind of think of environment variables like your custom desk setup.
Okay, I can see that.
You know, you have your specific chair height, your dual monitors, your custom aliases, your specific shell history. When you use su, you have to tell the kernel whether to bring your desk with you or to use the target user's desk.
That is a perfect analogy. And that entire architectural shift is controlled by a single character.
The dash.
Right, the dash. Yeah. The matrix on the slide maps this out perfectly.
Right.
Running su without a dash gives you UID 0 privileges, but it preserves your current standard user environment variables.
So you are basically sitting at your own desk but holding the master key.
Precisely.
But why would I ever want their desk? If I have the master key, why do I care if I'm using the root user's path variable?
Well, because many administrative binaries, like fufdisk or iptables, are located in secure directories like /spin.
Oh, right.
And a standard user's path usually does not include those directories. If you don't use the dash to load the root environment, you'll type a command and get a command not found error, even though you technically have the privileges to run it.
Because the shell just doesn't know where to look.
Exactly. The system is literally blind to the admin tools.
So adding the dash, typing su space dash, forces a full login shell. It completely overwrites your desk with the root user's desk.
Yep. And the matrix shows this applies to standard users too. Typing su-jsmith or su-ljsmith loads their full environment.
Got it. Knowing when to use that dash is critical for real-world troubleshooting.
It really is.
But sometimes you don't want to switch desks at all. You just need to reach over, hit one button on the root desk, and then pull your hand back.
The precision strikes.
Right. Let's go to slide 6, titled Precision Strikes with Single Commands. But I see the slide warns about 2 major syntax traps right out of the gate. The ABCD error and the cat error.
Oh, people fail the exam on these all the time.
If I type su ABCD to start a service, the system thinks ABCD is a username, right? Same with su-cat /etc/ /inittab. It thinks cat is a human.
Yeah, the shell parses the first argument after su as the target identity string. It doesn't analyze whether cat is a valid binary in your path. It just blindly checks the password file for a user actually named cat.
Okay, so how do we force the shell to parse it as an executable action instead of an identity? That is my challenge for the listeners right now. You are logged in as a standard user, but you need to read the contents of /etc/ /inittab, a file you don't have permission to see. Formulate the exact command using su to run this single command as root. Pause the audio and really think about it.
All right, so the correct syntax blueprint, which is right at the bottom of the slide, is this. Su space -c space quote cat /etc/ /inittab quote space -l.
Okay, let's break that down. I understand the -c switch.
All right, -c stands for command. It explicitly intercepts the shell's default behavior, telling it do not look for a user. Send the following string directly to the subshell for execution.
But why the quotation marks? Doesn't the shell inherently know where the command ends?
Actually, no, it doesn't. Without the quotes, the shell reads spaces as argument separators. It would try to run cat as the command, and then it would get completely confused about what to do with the file path in the context of the su wrapper.
Oh, so the quotes bundle the entire executable string into a single argument block so su can hand it off cleanly.
Exactly. It keeps it bundled.
Okay, that makes sense. But the real exam trap here is that -l at the end. Why do I need -l to just read a text file?
Well, the -l ensures the subshell spawned by su is a login shell.
Ah, back to the environment.
Yes. It sets up the proper pathing and environment variables before executing the command string. Depending on the command you are wrapping in those quotes, lacking the -l can cause the execution to fail silently.
It is a very tightly engineered sequence, isn't it?
Very tight.
But once that subshell finishes the precision strike, it terminates automatically. However, if you did a full switch, like if you used sudo and have been working as root for an hour, you have to manually sever that session.
You definitely do.
Which brings us to slide 7, titled Terminating the Disguise.
And the exam is going to test your absolute certainty on the commands that sever the subshell.
I see the certification trap listed here throws in some distractors.
Well, they love distractors. They'll throw in log off, which is a Windows command,
Right.
or break, which is used within shell scripting to exit a loop, but it won't drop your privileges, and off, which is just totally made up.
So the only valid commands to drop back to your standard user are exit or log out.
That's right.
Okay, so that is method 1. But, I mean, I have to play devil's advocate here for a second.
Go for it.
Handing out the actual root password to a dozen junior administrators seems like an archaic, massive liability. If su requires sharing the master key, why does it even still exist in modern distributions? Shouldn't we just ban it entirely?
Well, su still exists because sometimes you truly need a full, unrestricted environment shift, especially for deep system recovery.
Yeah.
But you are highlighting the exact reasons sudo was engineered.
Here's where it gets really interesting. Let's move to slide 8, titled Method 2, the VIP Hall Pass, which introduces sudo.
Yeah, sudo fundamentally changes the authentication mechanism. Instead of sharing a single master key, sudo acts as a cryptographic hall pass.
Well, I love that. A VIP pass.
It allows a standard user to execute a command as root without ever knowing the root password.
The visual on the slide is great. It's a standard user scanning their own badge at a security gate. The system isn't asking for root's password. It emphasizes that you are prompted for your current user password.
Exactly. It's verifying your identity against a pre-authorized guest list rather than making you prove, root's big secret.
And the execution is so much more streamlined. The PAM module for sudo doesn't require -c or quotation blocks for basic commands. You just prefix your action, like sudo yum install systat.
Yep. The system verifies your password, checks the internal policy matrix, and executes the binary with elevated privileges.
Let's lock this contrast down on slide 9, titled The Identity Matrix, su versus sudo.
It's a great summary matrix.
Su is the disguise. It requires the target's password and grants a full session by default. Sudo is the VIP pass. It requires your own password and grants power only for that single execution line.
Perfectly stated.
Time for another listener challenge. Pause the audio and answer this in 2 to 3 sentences. If an exam question specifically states that you do not know the root password, which elevation command is your only option, and why does its authentication mechanism make this possible?
So the only viable option in that scenario is sudo. The underlying authentication mechanism of sudo relies entirely on verifying the identity of the user invoking it, using their own credentials.
Right.
And then it compares that verified identity against the sudoers policy file to determine authorization. Root's password is mathematically irrelevant to the whole transaction.
But if it is checking a list and handing out root privileges based on individual passwords, the system better be keeping a meticulous paper trail.
Oh, it absolutely does.
Let's look at slide 10, titled The Audit Trail. The kernel isn't just blindly trusting the VIP pass. It logs the exact timestamp, the user, the working directory, and the exact command executed.
Accountability is the primary reason enterprise environments prefer sudo. This telemetry is all dumped into /var/log/security.
Okay, but I'm looking at the certification trap on this slide, and this is critical.
Yeah, the trap is assuming that only successful sudo executions are logged.
Right. The bouncer at the club doesn't just record who gets in, they record who tries to sneak in and gets rejected.
Exactly. That log file heavily tracks failed attempts. If an unauthorized user attempts to prefix a command with sudo, the kernel denies it and writes a high-priority alert to that log. Security systems specifically monitor that file to detect internal privilege escalation attacks.
Okay, so the bouncer has a list and logs everything. Let's talk about the list itself. Moving to slide 11, titled The Gatekeeper Protocol.
The infamous sudoers file.
Yeah, we see another heavy Valdor on the slide guarding the /etc/sudoers file. Now, my instinct as an admin is to just open that configuration file with a standard text editor. I use nano, vi, or gedit for everything else in /etc. Why is this specific file treated like a nuclear launch code?
Well, what's fascinating here is that a parsing error in that sudoers file results in a kernel-level lockout.
Wait, a complete lockout?
Yes. If you open it in nano, Make a single typo like a missing comma or an unclosed bracket and save it. The pseudo-binary will fail to parse the policy. It will crash every single time anyone tries to use it.
Oh, wow.
And if root login is disabled, which is best practice, and sudo is broken, nobody can elevate privileges to fix the file. You have effectively bricked the administration of the server.
That is terrifying. It is a single point of failure, so how do we mitigate that risk when editing?
By using the enforcer, the vsudo command. Yeah, you never edit the sudoers file directly. Vsudo is a dedicated binary that opens a temporary copy of the file in memory. When you attempt to save and exit, vsudo runs a strict syntax check against the buffer.
Ah, so it checks your work.
Exactly. If it detects a single structural error, it halts the process and refuses to overwrite the live file. It actively protects the system from human error.
Looking at the quiz intel in the corner, it says, if asked how to add a line to the sudoers file, any option that says edit with vsic or use vsudo/etc/hosts is a distractor. Run vsudo by itself to safely open the file.
That is a highly testable mechanism. You just type vsudo.
So vsudo protects us while we edit, but what language are we actually writing in this file? Let's go to slide 12, titled Deconstructing the Rulebook. This breaks down the syntax. I mean, it looks like a complex programming language.
It looks intimidating, but it's really just a system of 4 defined variables called aliases. It's essentially a logic puzzle.
Let's unpack the logic.
Sure. The first piece is the user alias. This defines the who. It is a variable containing a list of standard user accounts.
Right, so like JSmith or Sims.
Exactly. Now, the second piece is the host alias, which defines the where. In a massive enterprise, you might want JSmith to have restart privileges on the web servers, but absolutely zero access to the database servers. So you group host names or IPs into aliases.
Makes sense. The third piece is the command alias, or crummed alias. This is the what. Instead of granting blanket root access, you define the exact absolute paths to the binaries they are allowed to run, like /bin/rpm. You restrict the blast radius.
Yep. And finally, the Runus alias. This specifies the who as. By default, administrators assume sudo means running as root. But you can use a Runus alias to restrict a user so they can only execute commands as the Postgres database account, further compartmentalizing access.
So we have the who, where, what, and who as. Let's see them compile into a live rule on slide 13 titled Assembling a Security Policy.
This is where it all snaps together.
The syntax engine requires a very strict order of operations. User alias space host alias equals sign, then the Runus alias in parentheses, followed by a space, and the command alias.
Very strict.
Time to test your syntax translation skills. Listeners, look at the policy line displayed on the slide. Installers file servers equals open parenthesis root, close parenthesis, install. Pause the audio and decode this line. Who is getting access? Where are they getting it? Who are they acting as? And what exactly are they allowed to do?
All right, translating that logic. Installers maps to the user alias, identifying the authorized personnel. File servers maps to the host alias, restricting their authority to specific network nodes.
Right.
The root in parentheses is the Runus alias, granting them UID0 execution context. And install is the command alias, defining the strict list of allowed binaries.
There is a critical piece of quiz intel here too. If that Runus alias in the parentheses is completely missing from the line, what happens? Does the parser throw an error?
No, it doesn't fail. By design, if the Runus alias is omitted, the pseudo parser automatically defaults to root.
It just assumes UID 0.
Yep. So if you see a policy on the exam without parentheses, you must assume it implies maximum execution privileges.
Now, we have focused heavily on executing binaries, but what about modifying configuration files? I mean, if two admins use sudo /etc/hosts at the exact same time, they are both writing directly to the master file as root. It is a race condition waiting to corrupt the file.
It's a huge architectural flaw if you do it that way.
Right, which brings us to slide 14, titled Secure Drops and VIP Groups.
The kernel actually provides a dedicated tool for this called sudo edit. When you invoke sudo edit followed by a file name, it completely changes the file handling mechanism. It does not grant the editor root privileges.
It doesn't.
No. Instead, sudo edit copies the master file to a temporary file in/temp, sets the ownership of that temp file to the invoking user, and opens it using the user's default text editor.
Oh, so it's like a sandbox. You edit the copy using your own restricted permissions.
Exactly. And when you close the editor, sudo takes over, verifies the changes, and uses its root authority to seamlessly replace the master file with your modified copy. No race conditions, no locked files.
That is brilliant.
It really is. And managing who gets to use these tools is typically handled by Linux groups, rather than listing hundreds of users in the sudoers file.
Right. The slide mentions the wheel group.
Yeah, historically there is one group tied explicitly to privilege escalation, and that's the wheel group. The %wheel group is a legacy concept from early Unix systems, basically representing those at the wheel of the system.
So if you put a user in the %wheel group, the policy can grant them sweeping elevation rights. Let's test that syntax with a final critical thinking pause. Grab a pen. You need to add a line to the sudoers file that limits users in the managers group to editing the /etc/hosts.allow file using the secure edit method we just covered. What is the exact syntax you would use, and why is the very first character of that line so critical? Pause and write it out.
So the required string is %managers all equals sudo edit /etc/hosts.allow.
And that first character,
The absolute most critical element is the percentage sign prefixing the group name. The sudo parser uses that percentage sign as a discrete identifier.
meaning if you forget it.
If you omit it, the parser searches the password file for a single user actually named managers. The percentage sign instructs the parser to instead query the group file. It alters the entire logic path of the authorization check.
One character changes the entire security posture. That is intense. And that brings us to our final slide, slide 15, titled Pre-Mission Briefing, Top 5 Exam Directives. So what does this all mean? Let's run through this rapid-fire checklist before you sit for the exam.
Directive 1 is passwords. Sudo validates against the target's credentials. Sudo validates against your credentials via PAM.
Right. Directive 2 is syntax traps. Never use su followed by an action without the -c switch in quotes.
Directive 3 is the gatekeeper. The sudo file is parsed so strictly that it must only be edited with vsudo to leverage its memory buffer syntax checks.
Directive 4 is logging. The kernel audits everything in /var/log/security, specifically tracking failed escalation attempts for intrusion detection.
Then finally, Directive 5 is exiting. Terminate a spawn subshell cleanly using exit or logout.
That wraps the blueprint, the quiz intel, and the underlying kernel mechanics you really need to understand. You are ready to tackle these concepts in your labs, keep studying, map out those syntax structures, and ace those quizzes.
I will leave you with a final thought to mull over. If sudo allows us to grant incredibly granular, single-command access to standard users, logging every action without ever having to share the root password, well, will there ever be a future where human administrators don't even have a root password at all, and everything on the system is handled entirely by automated, hyper-specific policy matrices?
Something to think about next time you reach for that master key.